Good morning, students. So we are discussing with Einstein's photoelectric equation, and let us continue with that. So we have the expression kinetic energy is equal to h nu minus nu naught, isn't it? Where nu is the frequency and nu naught is the threshold frequency, and then h nu naught can also be called as work function phi naught. So this expression can also be written as kinetic energy is equal to h nu minus phi naught. Okay. Now today we are going to discuss first the relation between stopping potential, that is V naught, and threshold frequency nu naught. Okay, this is V naught, that is stopping potential, and nu naught, that is threshold frequency. So we can start with Einstein's photoelectric equation. So the equation is kinetic energy is equal to h nu minus nu naught. Okay, that is kinetic energy is equal to E V naught. This is the condition for stopping potential. So instead of this kinetic energy, I can write E V naught, which will be E V naught equals h into nu minus nu naught. Okay, then if lambda is the wavelength of incident radiation, then you can call lambda naught as the threshold wavelength. Threshold wavelength, as we told threshold frequency, lambda naught can be called as the threshold wavelength of the metal surface. Okay, then c is the velocity of light. C is the velocity of light. So lambda is the wavelength of the incident radiation. Wavelength of the incident radiation. Then lambda naught is the threshold wavelength. C is the velocity of light. Okay. Then you can write nu is equal to C by lambda. Similarly, nu naught is equal to C by lambda naught. Isn't it? So you can put the values of this nu and nu naught in our first equation, that is in this equation you can substitute the values of nu and nu naught. So this expression will turn to E V naught, which is equal to, you are substituting in equation number 2. Okay, so 2 will change to E V naught is equal to h into C by lambda minus C by lambda naught. Okay, so from this expression E V naught is equal to, you can write as hc into 1 by lambda minus 1 by lambda naught. Clear? So this is the expression or relation between stopping potential V naught and also the threshold frequency as well as threshold wavelength. Okay, so this expression you should keep in mind, needed for numericals. Clear? So next we are going to verify the laws of photoelectric emission based on Einstein's photoelectric equation, because as you have seen, we got certain laws from photoelectric emission and wave theory couldn't explain it. Okay, at that time Einstein's photoelectric equation came into existence, and now how this photoelectric equation by Einstein is used to explain or to verify the laws of photoelectric emission. Okay, so we will start with the equation. Our equation is kinetic energy is equal to, or half m v max square is equal to h into nu minus nu naught. This is Einstein's photoelectric equation. Now how this equation is used to explain each point. So actually this equation successfully explains the laws of photoelectric emission, and first point is like this, that is, in this expression, if the value of nu is less than nu naught, okay, if the value of nu, that is frequency of incident radiation, is less than the threshold frequency, then you can write in this expression, if this is less than this value means this will turn to negative, isn't it? So kinetic energy will become what? It is negative, and it is not possible. Okay, kinetic energy will turn to negative according to this equation, which is not possible. Therefore, for photoelectric emission to take place, this condition should be like this: nu must be greater than nu zero. Then only photoelectric emission takes place. Understand? So in this expression, or with the help of this equation, he could explain like this, that is, if the value of frequency of incident radiation is less than the threshold frequency, then in this equation, if you are substituting, kinetic energy will become negative, and so it is not possible, which means that nu must be greater than nu naught, then only photoelectric emission will take place. Understand? Now the second point is, since you know one photon, if in a metal surface, if one photon is able to emit one electron, okay, one photon emits one electron, then the number of photoelectrons emitted per second is directly proportional to the intensity of incident light. Okay, that is the number of photoelectrons emitted per second. Number of photoelectrons emitted per second is actually directly proportional to what? Is proportional to intensity of the incident light. Okay. Now the third point is, half m Vmax square is proportional to nu, isn't it? From this expression you could understood that half m Vmax square is actually, h is a constant, Planck's constant, so you can write it is proportional to the frequency, right? So here h and nu naught are constants. Since h and nu naught are constants, half m Vmax square must be proportional to nu. So what does it indicate? This is kinetic energy and it is frequency, isn't it? So as we told in the last class, kinetic energy of the photoelectron is directly proportional to frequency. Kinetic energy is directly proportional to frequency, but this law cannot be explained with the help of wave theory. You are remembering, right? So half m Vmax square is proportional to nu. So kinetic energy proportional to nu. Again, this shows that kinetic energy of photoelectron is directly proportional to frequency of the incident light. Then the fourth point is with respect to time. You remember that. That is, photoelectric emission is actually, it's a collision, right? And it is an elastic collision. It is said that it is an elastic collision between whom? As photon and an electron, isn't it? It is an elastic collision between photon and an electron. So as such, there cannot be any significant time lag between the incidence of photon and emission of photoelectron. Okay, so it is an instantaneous process. Clear? So this Einstein's photoelectric equation could explain or could verify the laws of photoelectric emission that we have already seen. Clear? Now there are certain graphs related to photoelectric effect from Einstein photoelectric equation. So let us go through it. So the first graph related to photoelectric effect is the graph between frequency nu and the stopping potential V naught. Okay, frequency nu and stopping potential V naught. So this expression we already discussed, that is E V naught is equal to h nu minus phi naught. From this, what is V naught? H by E into nu minus phi naught by E. Okay, all these are constants. E constant, phi naught, H, all are constants. So I can write V naught proportional to V. What does it mean? Stopping potential is directly proportional to frequency, isn't it? Stopping potential is directly proportional to frequency. So if I am drawing a graph like this, okay, this is stopping potential. And here we have frequency. So we will get a graph like this. It's a straight line, okay. That is, makes an angle theta. This is the threshold frequency above which the emission takes place. Then if you are extending it, you will get here, which is minus phi naught by E. Okay. Which is the y-intercept, isn't it? Now, in this equation, you can see that V naught is equal to h by E nu minus phi naught E can be compared to y equal to mx plus c. Isn't it? Y equal to mx plus c, which is the equation for a straight line. Right. So, from this equation, what is m? M is the slope. Okay. So, here slope is given as tan theta, which is equal to h by E. Isn't it? Tan theta is equal to h by E. Clear? So, it could be seen that here V naught versus nu curve is a straight line with slope h by E, and it is independent of the nature of the material. Okay, it is independent of the nature of the material. Clear? So, this is the graph between frequency and V naught. Okay, from the graph we got the constant value, that is the intercept, as minus phi naught by E. This also we are getting from the equation, because this can be compared to y is equal to mx plus c, where m is the slope h by E. Okay, this is variable, right? Then this value is given as minus phi naught by E. Okay, moving to the second graph. Second graph is frequency nu and kinetic energy maximum. Okay, frequency nu and kinetic energy maximum. So again we are drawing a graph like this. Here we have the kinetic energy, maximum value of kinetic energy, and here we have the frequency. We are getting a graph like this. Okay, making angle theta, tan theta. You have to find from where you will get tan theta. Let's write the equation for kinetic energy and frequency. That is, kinetic energy is equal to h nu minus phi naught, isn't it? So, what is this? This, if we are comparing this to the equation for a straight line, this is actually equal to mx plus c. So, what is slope here? Slope is h. So, tan theta is h. Okay. So, now how can you write this equation? Kinetic energy proportional to nu. Okay. What does it mean? Yes, kinetic energy is directly proportional to the frequency. So again you are getting the graph like this. Clear? So what is this value? It is minus phi naught. Minus phi naught. Clear? Okay. So now we can conclude, that is, there is a particle nature shown by light which we call as the photon, isn't it? And photoelectric effect thus gave evidence that light consists of packets of energy, and these packets of energy were called light quantum, that are associated with particles named as photons. Okay, so now you understood what are photons. And these photons actually confirm the particle nature of light. Photons confirm the particle nature of light. So the energy of a photon is given by, what is the value? As it is h nu. H nu is the value, or you can write hc by lambda. Okay, h is the Planck's constant, nu is the frequency of radiation, c is the speed of light, lambda is the wavelength of photon. Also the momentum, if it is a particle it should have momentum. Momentum is given by E by C. What is E by C? H nu by C, isn't it? H nu by C. And what is nu by C? It is 1 by lambda, that is h by lambda. Clear? H by lambda. So these are the expressions for energy of a photon as well as momentum of the photon. Okay. Now what are the properties of photons? So we can take a note of the properties now. Already we have discussed in the first class like a general introduction. Anyway, the characteristic properties of photons are there. So first property goes like this. First property is when the radiation interact with matter. When the radiation interact with matter, radiation behaves as if it is made up of particles called photons. Understand? When suppose this is the matter, okay, when radiation interacts with matter, this radiation behaves as if it is made up of particles called photons. Now what about the speed of photon? As it is 3 into 10 power 8 meter per second in air or vacuum. This is the speed of photon. Now as I told, it has zero rest mass. Zero rest mass. That is, the photon cannot exist at rest. So when we discuss the theory of relativity and all, when you are moving to your higher classes, you will study that the mass m of the particle moving with velocity v comparable with the velocity of light c is given by one expression, that is m is equal to m0 by root of 1 minus v square by c square. You will study this in theory of relativity. And from this expression, what is m0 or m0? It is m into root of 1 minus v square by c square, where m0 is the mass of the particle at rest. So m0 is the particle mass at rest. Okay. Then if a if a photon moves with the speed of light, this value will be 1. Because this is also equal to c, right? So what is m0 or m0? Yes, m0 will turn to 0, which means that the rest mass of photon is 0. Rest mass of photon is 0. That is, the photon cannot exist at rest. Understand? Okay. Now the next point is the mass of the photon, inertial mass, you can call like that. Inertial mass of the photon is given by the expression, you know, that is E is equal to mc square, right? So what is m? M equal to E by c square or h by c lambda. Or you can write it as, for lambda, you can write it as nu by c, that is c square, h nu by c square. Clear? Next point is photons travel in a straight line. Photons travel in a straight line. Okay. Then energy of a photon, of course, it depends upon the frequency. Energy depends upon frequency of the photon, and the energy of photon does not change when photon travels from one medium to another. Clear? Next, wavelength of photon changes with respect to the media. Okay, in different media, the wavelength of photon changes. Wavelength changes in different media. Okay, in different media, and velocity of photon will also be different. If the wavelength is changing, velocity also will be different in different media. Okay, velocity also change in different media. The next one, photons, as I told, they are electrically neutral. Electrically neutral, which means that they will not get deflected by the electric and magnetic field. Electrically neutral. Clear? And in a photon particle collision, you can say the energy and the momentum are conserved. If energy and momentum are conserved, it should be an elastic collision. Okay, so the number of photons may not be conserved, but the energy as well as momentum, if it is a photoelectron collision, these two factors will get conserved. Understand? So these are the characteristic properties of photons. Characteristic properties of photons. Understood? Once again, in interaction with matter, interaction of radiation with matter, the radiation behaves as if it is made up of particles called photon. Then a photon travels with a speed of 3 into 10 power 8 meter per second. Then it has zero rest mass. Okay. Then the inertial mass is given by the expression m equal to E by c square or h nu by c square. Then photons travel in a straight line. Then energy of a photon depends upon frequency of the photon. Wavelength will be different in different media, so that the velocity will also change in different media. Then photons are electrically neutral. Then we can say that it is an elastic collision in which the energy and momentum are conserved. Okay. So next we are going to discuss about a device which we call as photocell. Photocell. Okay. Photo means what? Light. So actually this device converts light energy into electrical energy. So photocell, use of photocell is it converts light energy to electrical energy. Okay. Now, a photocell actually consists of a semi-cylindrical photosensitive metal plate C. Semi-cylindrical photosensitive metal plate C, which we call as the emitter or cathode. Okay. And a wire loop A. A wire loop A we call as a collector, and it is supported in an evacuated glass or quartz bulb. When light of suitable wavelength falls on the emitter C, photoelectrons are emitted. Understand? So, as the photoelectric current sets up inside the photoelectric cell corresponding to incident light, it actually provides the information about the objects as has been seen by our eye in the presence of light. Okay, so here the photoelectric current, when these photoelectrons are emitted, photoelectric current is generated, and this photoelectric current which is generated in the photoelectric cell corresponding to incident light, it provides the information about the objects as has been seen by our eye in the presence of light. Now what are the applications of photocell? First application is it is used in television camera. Okay, it is used in television camera for telecasting scenes, and also in phototelegraphy. Second one is reproduction of sound. Okay, reproduction of sound in camera film. Next is third, used in counting devices. Counting devices. Used in the burglar alarm or fire alarm. Also to measure the temperature of stars. Finally, it is used for the determination of Planck's constant. Okay, it is used in the determination of Planck's constant. Clear? So that's all about the first section in this chapter, that is the particle nature of light. We have discussed clearly with the help of photoelectric effect and also Einstein's photoelectric equation. Very important. So study well. Okay. Now the second section is, we have told that this matter also exhibits two properties like particle nature as well as wave nature. So particle nature you know, because common only, you have studied in your smaller classes. And finally we are moving to the wave nature of matter. Wave nature of matter, which we call as the matter wave. Okay, so our topic is matter wave.